last big, let's say, group of editing or adjustments you can make to an image, and these are geometric adjustments. So when you are changing the resolution, the shape, or when you are rotating the image, and so on. First of all, the nomenclature is not very clear in here, so it's always a good idea to make sure that you are communicating in a bomb-proof way. But there are three important measurements or variables to distinguish. First, the actual size in pixels. However, mm, like awkward it sounds, it's for me the size in pixels is the uh, clearest way of representing that. It is just the amount of pixels given in width and height of well, just saying how big the raster that the image is represented by is. This is the only true size of the image. This tells you like how many pixels you have. This is the information you have, and this is the true size of the image. Even though it's only it's, of course, pixel is, let's say, a mental construct. It's not a physical object that you can measure with a ruler, but this is the true size of the image. And by the way, you can, of course, just by multiplying these two numbers, you get the total amount of pixels in your image, which is the count in megapixels that is used to describe the resolution of camera sensors and so on. Then we have print size, or like the intended physical size of the image. This is just saying how big we think the image will be when we print it out. Uh, it again, I am stating it here in this commentary. It is not you can in no way tell from the image itself, just when you see the picture on your screen, how big it should be when you print it. So this is the role of the metadata. So the other non-image information saved in the image file, where you can find the information what was the intended print size. Uh, it is, but it is not a good idea to rely on this information, because usually the users or the people whom you are getting the image from will not bother very much making sure that the intended print size is correct. So when you are having something printed or working with it like this, don't rely on these information in the metadata, and it's always better to ask and not just to look, because not many people know that the information of the intended print size is in the metadata, and they might ignore it, or there can be some nonsense information there. And the last part of the equation is the resolution, or but because, well, this is what we call a resolution on the computer screens and so on. So calling this the resolution is, again, it can be confusing. So usually I just prefer you calling it the DPI value. DPI means dots per inch, and this is just the ratio between the size in pixels and the intended print size. So if we have an image of let's say 500 by 300 pixels, and we print it at 100 dpi, meaning 100 dots per inch, it means that it will be 5 times 3 inches when we print it. Again, the same applies. It is not a good idea to rely on the information on the DPI that determine the print size. It is always good idea to verify the intentions of whoever produced the image. Usually there is only one value of DPI because it is assumed that the pixels are square, so the DPI would be the same for the width and the height. It's not always the case, but it's mainly for some old video formats where actually non-square pixels were present. There are some typical values of the DPI that are used, like the generic screen values, so-called, that were like by most programs used when you were creating RGB files for use on the screen, not for prints, was either 72 in older versions of the systems, which then I think with like Windows Vista or sometimes around that changed to 96 DPI. But this is basically a placeholder value. This is by no means, of course, a standard. It may be approximately it may approximately correspond to the actual DPI of a computer screen, but not exactly. So I've seen to my quite a substantial surprise in some copy shop where I actually had my I think a diploma thesis printed out. When the guy there was dealing with the previous customer, they were, I think, they were preparing some graphics to be milled for some kind of heavy metal stamp or some stamping die or something like this. And when the customer asked him like what is going to be the final size, the guy just set the scale on his computer screen to 100%, took a ruler and measured it on his screen. So yeah, don't do this. The resolution of your computer screen is basically an unknown, so you cannot measure things on your computer screen. It's not a good idea. Typical DPI values for printing are either 150 for, let's say, basic quality, or 300 dots per inch, which is just like the accepted standard for quality prints, and usually for regular images, photos, and so on. Nobody would want more than 300 dots per inch. The only difference is line art, and this is a term that you quite often encounter in instructions to authors from scientific journals. Line art is basically, if you are familiar with using a pen and ink to draw, that with the pen you have no possibility of making darker or lines or lighter lines or whatever. So line art is basically anything which uses basically monochrome, just white and black, but with where the let's say areas are stripe, where various striping are used to shade the areas and so on. Yeah, so this is it. Just DPI determines basically, of course, how densely your information, the actual count of pixels, will be placed on the physical medium, usually printed. So this is a way how to judge how many pixels your image should have in order for the result to be good. So if you know that you let's say in the article that it will most likely be a chart that will be I don't know, 10 centimeters. So let's say 10 centimeters is 4 inches, then the reasonable minimum for this would be 300 dpi times 4 inches is 1200 pixels width should be the minimum. However, if it's a chart or if it's a graph, um, it is usually better to consider it close to line art, so I will go at least for 600 dpi, because the important, bringing us to the next slide, the important note is that you can always reduce the size of the image. You can always just shrink it, throw away the information you don't need. But once it is small, you can never make it bigger with the sufficient amount of details. Of course, you can sort of inflate the image, but it gets blurry. So there is no easy way how to enlarge it. So I always prefer to work with the highest resolution that is reasonably possible when you are editing raster or bitmap images, which you can always, when you are done with it, you can always shrink it back. Just a practical note here is that resizing an image by a small percentage can be risky, because some of the algorithms, most of the algorithms work well if you are reducing the image, let's say, to half of its size, then it will look very nicely. But if you, let's say, just shrink the image by 3% or something like this, some of the algorithms can produce like not very nice results, and there can be some artifacts. So try to avoid resizing image by a small percentage. Okay, now resampling. Resampling, well, generally speaking, very generally speaking now, sampling is a process that you do to represent a continuous information by a set of points. Sampling is done, let's say, when you are recording audio signal, when you are recording sound, that of course these sound waves are from the physics point of view, are a completely continual changes of acoustic pressure. The computer records it as taking samples in the, let's say, in the general CD type audio, it's like 44,000 measurements per second. And for each of this measurement, the value of the pressure or of the deflection of the microphone membrane or whatever, the intensity of the sound is recorded. So sampling is whenever we represent a continuous information with just discrete measurement points. The same applies to images, because of course the image is not, I don't mean the original electronic image saved in our computer, but the actual physical image or the information that it should represent is continuous. But when we are using raster graphics, we are reproducing this continuous reality with just some points, with the pixels. Well, and a problem arises that when you apply some change of geometry, either you decrease the size of the image, you want to shrink it, or you want to enlarge it, or you stretch it, you rotate it, and so on. The problem is that our computer screens always have their pixels aligned vertically and horizontally, and all of them are square. And all the image formats work with this, that the pixels always are just straight vertical and straight horizontal. So when you do a 5% rotate or 5 degrees rotation of the image, like this is not 5 degrees, but as you can see in this picture, whenever you rotate it, your let's say you have the information what the color should be in each of these cells in the original, but when the original is rotated and you confirm the information, because the image can only be represented in these straight columns and straight rows of pixels, the computer or the program needs to somehow calculate or recalculate the values in the new output grid, the solid one, that would represent the input grid, which was just twisted, or it can be shrunk, enlarged, whatever, so that the color of these new output pixels would represent the old pixels in the, let's say, most visually pleasing way. And here we have some just illustrations of the basic algorithms. The easiest one and also the quickest one to calculate is called the nearest neighbor. And this is just that the new pixel here, A, gets assigned the value that was originally in the which is in the which was in the pixel that is now transformed to be the closest one. That's why it's called the nearest neighbor. The next one is called bilinear interpolation, and this already uses these like the information from more than one of the original pixels and tries to somehow find a compromise between them. And another example here is cubic convolution and so on, where the region is even bigger, and it can also detect like what were the trends in the original region and try to guess the best value for the new pixel. By the way, I found this example, this image, only with the rotation of the image, but the same applies only when you just shrink the image. Uh, Again, you have like two geometrically different grids on top of each other, and you are trying to fill the output one based on the proximity and values of the values in the input one. Yeah, just so now to let's say to summarize the resampling problem. So yeah, there is a lot of different programs to do it. And yeah, my practical advice here is that when you are editing, just always make sure to choose the best one. It's usually in the programs, it's usually noted there that this is like the best one, the highest quality and whatever, because unless you are doing something really special, or you dealing with very big images, today computational speed is not really problematic even for the high quality algorithms. And another important note is that if you are zooming an image on your screen, then this basically like displaying an image on your screen in any than the original 100% 1:1 pixel scale. Like each program that can show enlarged or reduced size image needs to use some resampling algorithm. So for example, even if for example, even if you go to an internet browser here, and this is the page for the PaintNet program, and you see, for example, that this logo or this download button uh, is an image. So when I zoom in here, you see that there is something going on. So because it is not very blocky and squarish, we can see that it is not probably a nearest neighbor algorithm. but I would guess that Google Chrome here uses the bilinear interpolation algorithm. So this is it. So this is just a advice that when you are in some image, let's say you are if you use Windows, the default Windows images or the different the default Windows viewer for photos. So here, when I zoom in, let's see what the algorithm is. Yeah, it is not very apparent in here, but this also uses some sort of interpolation, so you don't see the individual pixels clearly in here. Maybe this is a good idea to go to the practice in PaintNet again, and let's say we can start we can start with the letters example. So this is just an image containing just black and white letters, and the easiest way how to try the effects of different algorithms is just we can either in here in image and resize image. We can change the size of the image, and we can choose here the algorithm that we want to use. But what I like to do more, because I think it's a little clearer, we can just take a selection tool, make a selection of some image data of some pixels, and then if we switch here to the on the panel of tools, if we switch to this white move selection tool, we can, besides moving, I'm sorry, not the move selection, the move selected pixels, the dark blue one, we can use on this rectangle, we have this, let's say, grabbing points, and we can use them to transform just this selection of the image. And as you are using it, don't worry, even if you let go, the change is not made until you hit the finish button here or hit enter. So you can try, and it's still using the original information. And here we have the quality, and here you see that in this, let's say, live editing, or if you are using just this selection transformation, the selection of the resampling algorithms is limited. But again, these are the three most common ones: the nearest neighbor, bilinear, and bicubic. And you can just, by switching through them, you can see the different results. And so the nearest neighbor is the by far the blockiest one, because it never blends the pixels together. It only chooses the nearest neighbor. And the bilinear and bicubic, on this actual example, the reason the difference here is not very big, but generally the bicubic produces sharper and nicer results. We can also try the same thing in here with the B letter, which you can see is represented a little bit differently. I will talk about it in just a second. But again, if we make a rectangular selection of the pixels, then switch to the move selected pixels tool, and then we perform the transformation. Here you can see very nicely then that originally there are no gray pixels in between the edges. There are no no smoothing going on here, and this is only black and white. But when we enlarged and inflated it with BigCubic, the BigCubic tried to put some grays, some shading of gray to the borders to make the transition smoother. Billionaire does the same, but only not as nicely, I would say, and not as sharply. But as you see with the nearest neighbor, it never tries to blend or to smooth anything, and it's still sharp and blocky because effectively it is just growing the pixels that were originally present. Okay, so this is the difference between the resampling algorithms, so that if you mainly the place where you will encounter it is that when you do the here in PaintNet, when you do image and resize, when you are resizing the image, so that you know that basically the easiest way how to do it is to just do to choose the best quality, because it rarely slows you down in any way, but just to be sure that it's selected like this. Okay, now I will just go back in the history to the point to the unchanged image, and I will talk briefly about the difference between the A and the B letters from the graphical point of view. As you see here, the letter A is somewhat smooth, and on the edges of the letter there are some gray pixels. The letter B is made with black and white pixels only, and it is I think that you can't see it very well through the Microsoft Teams transmission, but if you have a look at the image elsewhere and on your own computer, I think that in the 100% scale, you can see that the B, you can still see the individual pixels, and that it doesn't look very nice and very smooth. But on the letter A, it looks very nice even in 100% 100% scale, and this is because of the smoothing, and this is a process so-called anti-aliasing. You can see it here in the PaintNet. Actually, when I decide to write any text into my image, uh, I will select the text tool, place the cursor somewhere in the image. Before starting to type, I will make my font size bigger, just so that it's easier to see. And as you see that as I write a letter here, that by default I will go back to 100% scale. We can even change the scale a little bit more. Or we can do to 200, which should look which should look better through the Microsoft Teams. But as you can see, the smoothing is now on, the anti-aliasing is now on in here, and the contours are softened by the presence of the gray midtones. Here in this control on the tools panel, you can change between different types of anti-aliasing, because there are again multiple algorithms that can just change, but these are usually minor changes. And here, this control with the, let's say, crooked line and some control points in the icon, here you can choose between using the anti-aliasing or not using it. And what anti-aliasing does is precisely it tries to smooth, to make the things look and curves look smoother, even when displayed through the inherently discrete pixel grid of a computer monitor. By the way, the anti-aliasing is a term that is used really widely across all fields of computer graphics. If you play computer games, mainly like 3D graphics computer games, there is usually the anti-aliasing option, which if you enable it, you don't see the individual pixels because it's like the transitions are smoothened out. And it's in a lot of places, also in editing graphics like this. And by the way, in uh, PaintNet here, it's not only for text. Even though for text there are really special types of anti-aliasing, because the legibility of letters can be really affected by anti-aliasing. So it is really important for text. But even if let's say when I draw, when I do any basically transformation, or it would be easier to see with a circle. And let's say I will do a 2-color circle like this. So you can see that again, by default, the anti-aliasing is turned on, and I still have the option to turn it off. Let's say if we can, I can even zoom further to show you that here anti-aliasing is off and the outline of the circle is made is made only with red and black pixels. Here anti-aliasing is on and all the shapes are smoothed together. And basically anti-aliasing is, and that's why I have sort of shoehorned it into this part of the course, is that it is very similar to resampling in the way that in the resampling you are here you are trying to figure out the value in the output grid based on an input grid. And anti-aliasing is very similar in that you have the output grid, but instead of the input grid, you have the vector object, the imaginary perfect circle that you want to, or the perfect shape of the letter C that you somehow want to represent with the output grid. So instead of the input grid, you have the actual, let's say, vector shape of the thing that you want to represent with these pixels. And well, if you basically analogically to the nearest neighbor algorithm, if you just let's say if the letter covers more than 50% of the pixel, let's make it black. If it does not cover more than 50 pixels of percent of the pixel, let's make it white. This is the analogically to the nearest neighbor algorithm, which is with the anti-aliasing off. And analogically to the better resampling methods, when you are considering the actual shape and sort of averaging the surroundings of the pixel to get the visually most pleasing color to put there and to make a smooth gradient. This is analogic to the anti-aliasing being on. So yes, this is it. I believe for image size in PaintNet. Maybe another important note here, so just you are not confused. We have basically two different functions here to changing the size of the image. We have already used the image resize option, and that is that the image stays as it is and is either stretched or shrunk to the new dimension. So we can we can try to changing it, let's say, to a half of the original size. And all the objects are there. It is just smaller. We have shrunk it. On the if I go if I go back, then of course there is the canvas size option, and here you either crop the image, so the objects, the pixels that the image consists of will stay exactly the same. You are not enlarging anything or shrinking anything down. You are either just cropping the canvas of the image or adding blank space to the outside of the image. So we can demonstrate. So if I shrink it to 50%, it means that I will crop most of the outer parts of the image and only the middle C letter will remain there. And vice versa, if I make it bigger through the canvas size option. By the way, here you can select if you want to expand it or again contract it, like from or to the middle, or if you want, let's say, the bottom corner to be fixed and to shrink it with respect to it. So basically you are selecting the anchor point, which will stay the same. So for example, here when I select it like this, the letter A will still be in the corner of the image, but there will be blank space added to the right and to the bottom, like this. And the way why it is red is because my secondary color was selected red at the time that I did this operation. So I think that this pretty much covers the section on editing images geometrically with respect to color and with respect to brightness.